square? Is it polynomial?
There are a lot of problems in this series,
And if you work it out,
Yeah.
We are ready for our next speaker, Sarah Trebat-Leder from Emory University. The title of the talk is Moonshine from Mathieu Group 2022.
Okay. So this, let me get the mouse off the screen. So this is a new project that I've been working on. There is not a preprint yet. That will be hopefully pretty soon. This is the first time that I am talking about these results. So let me first start by talking about some sporadic groups. So if you remember the classification of finite simple groups, there are some that don't fit into any of the infinite families, and they're called sporadic groups. And the biggest of them is the monster group. And so the monster group has about 8 times 10 to the 53 elements and 194 conjugacy classes. And most of the other sporadic groups are related to the monster group. So another one is the Mathieu group M24. And it is a subquotient of the monster, but it is not a subgroup. And so this is kind of relevant because if it was a subgroup, it would be possible to get a moonshine for M24 to M23 that kind of trivially came from the monster group. So the Mathieu group M24 has about 2 times 28 elements and 26 conjugacy classes, and it's a permutation group on 24 objects, hence the 24. But the group we're actually going to be working with is M23, which has about 10 to the 7 elements and 17 conjugacy classes, and it's a point stabilizer of the action of M24 on 24 points. So if we want to look at the ones that fix one particular point. And so I'm going to start off with monstrous moonshine. So all modular functions on SL2Z are generated by J of tau. This is kind of a basic fact about modular forms. And when I say generated, I mean generated as rational functions. And so we say that J of tau, because of this property, is a principal modulus, or a hot module, and that SL2Z has genus 0. And so you can say that in general about other congruent subgroups. If they have some function that behaves like J of tau, then you say that it has genus 0. And I also want to note that we often normalize this and other principal moduli. We like to normalize it as q to the negative 1 plus O of q, so without any constant term. And that makes it unique. So the conjecture of Conway, Norton, and others is that there exists an infinite dimensional graded representation, noted as B natural, of M, such that the graded traces on this representation are principal moduli for genus 0 congruent subgroups, which we'll call gamma G. And the notation with the natural and the TG is not standard, but I decided to include it so that we can differentiate between the different graded traces in this talk, because we're going to be talking about different groups. And so to give an example, if we let G be the identity element, and I'm always going to denote conjugacy classes of the monster. Let me just let's not use this. I'm going to denote conjugacy classes of the monster as with capital letters, also just to kind of keep things clear. So then the graded trace of the identity element looks like this. And so by graded, so the q to the first term tells us the first kind of graded component. And this is, so since we're looking at the identity element, this just tells tells us the graded dimension, so the dimension of the first component. And this is the normalized principal modulus for SL2Z. And we can also see so you see that this 196884 is equal to 196883 plus 1. And these guys are dimensions of representations of the monster group. And the same thing for the second coefficient. So that we can break it up into dimensions of representations of the monster group, of irreducible representations of the monster group. And this is how monstrous moonshine was first noticed. So if you see the number 196884 and the number 196883, you kind of notice that, hey, look, they're close together. And this is kind of how monstrous moonshine got started, by noticing these guys. And so monstrous moonshine has been proven. So the first kind of thing towards a proof was a weak version. So a weak version means that you show that such a representation exists, but you haven't constructed it, and you don't know the geometric structure. And this was mostly done by Atkin, Fong, and Smith. They didn't completely finish this. They kind of left a computation that still needed to be done. But that train of thought stopped once there was a strong version, which means that we actually constructed the module, and this used VOAs, or vertex operator algebras. And so Frankel, Lukowski, and Merman constructed the VOA, and then Borchards proved the full conjecture. So the Frankel, Lukowski, and Merman only showed for G being the identity element, not all conjugacy classes. And this was a big, really big result. Borchards, got the Fields Medal in part because of this work. So this was a really, really important result. And so monstrous moonshine has become important to theoretical physicists. So lying behind it is a certain conformal field theory having the monster group as a group of symmetries. So if you go to a conference about moonshine, there's going to be a lot of string theorists, a lot of physicists saying words that, at least for me, I was not very familiar with, and I had to kind of learn what these things were. So the physicists are really interested in moonshine. So my theorem is that there exists an infinite dimensional graded representation of M23 whose Mackay-Thompson series are principal moduli for monstrous genus 0 congruent subgroups. And they're normalized differently. They have a different constant term, but they're really the same functions. And so here is how they match up. So over here we have the Mathieu group M23, and here we have the conjugacy classes of the monster that they correspond to, and here are our genus 0 subgroups. So both of these guys correspond. Both of these guys, their graded traces and the corresponding moonshines are going to give principal moduli on these genus 0 subgroups. So where does this come from? Oh, before I do that, let me give an example. So for the identity element, we have that the graded trace, also known as a Mackay-Thompson series in general, is the J function minus 744, which is what you get in monstrous moonshine, and then plus 48. So I kind of separated them out. So this gets rid of the constant term, and now we have a new constant term, 48. So this is just differs from our regular monstrous moonshine graded trace. And this is kind of how it breaks down. So here's our 196884, and according to any kind of moonshine, this tells us the dimension of the first graded representation that's part of our infinite dimensional module, and this breaks up as a sum of irreducibles, and this is how it breaks up. So the numbers in red are actually all of the irreducible representations of M23. And this is pretty ugly. So it's a lot more complicated than in monstrous moonshine. And really the reason is because this number is really big compared to all of the dimensions in here. But it's kind of the same thing. And it would be hard to notice it using this. It would be hard to be comparing the coefficients of our function to the degrees of the irreducible characters and see that there was a connection. So there's something else kind of where this comes from and how I had found out about it. And so this comes from Mathieu moonshine. So we started out looking at the Mathieu group, M24. So there already is a moonshine for the Mathieu group. So it exhibits moonshine where the Mackay-Thompson series, or the graded trace, are these Hg, which are weight 1/2 Mach modular forms. So here's an example for the identity element. This is what the H1 looks like. And the numbers in red are all dimensions of irreducible representations for M24. So in this case, it's very easy to see the connection between this function and M24. Well, if you looked at the function and the character table for M24, you can see the connection. So Gannon verified the existence of a module for the Mathieu case, for this case. So we don't know how to construct it yet. We don't know what the geometric structure is, but we know that it exists. Chang, Duncan, and Harvey generalized it to something called umbral moonshine. And the reason that this umbral comes up is because these are Mach modular forms. And a Mach modular form is a little bit more complicated than a modular form. And it has something called a shadow. And so that's where the word umbral comes from. And so Duncan, Griffin, and Ono verified the existence of the module for the rest of the umbral cases. But again, there's no geometric representation or interpretation so far. So the physicists are not happy. The representation theorists are not happy. The number theorists are okay. We're good. So these Hg of tau, they're something called a Rademacher sum. So a Rademacher sum is a regularization of a Poincare series. And a Poincare series is kind of a way to, if you have a function that you want to be symmetric, one thing you can do is you can sum it up over all of the action of all the symmetries on that function. And so that's kind of a general method for making a symmetric function. So if you want to make a function that's modular in a certain subgroup, you can sum it up over the action of that function of the subgroup on the function. And so that's kind of what a Poincare series is. And a Rademacher sum is how you deal with it when it doesn't converge. It's a way to make it converge. And when you regularize it to make it converge, in general, you lose modularity, and you just have something that's Mach modular. And so a Rademacher sum, if you pick a weight, and you pick a congruent subgroup, and you pick a principal part, and you pick a multiplier system, there's kind of a general way to get a function, to get a Mach modular form. And this multiplier system, epsilon, is just the same. Epsilon is the multiplier system of the eta function. So this is related, has a similar multiplier system to the eta function. And so if we let d and delta be 1 mod 8, where delta is less than 0 and d is greater than 0, this Rademacher sum is actually part of a much bigger family. So we can choose different principal parts, and we still get Rademacher sums. So actually, this Rademacher sum is just the d equals 1 case of this general family. And there's also a general construction about Rademacher sums, where if you take a family like this, and you think of each function as a row in a grid, you can look at the columns instead of the rows. And you can can get a dual Rademacher sum, which has these same coefficients, but instead of summing over delta, now we're summing over d. And our principal parts are going to be delta over 8 instead of negative d over 8. So you can think of a big grid of functions where these are the rows and these are the columns. And so since this has weight 1/2 on gamma 0 of ng, where ng is just the order of our element g, then our f is weight 3/2. And a priori, it's only a Mach modular form. But we can prove that it's in this particular case, it's actually a modular form. And so, in general, so for all of M24, you can do something similar, but the multiplier system is a little bit more complicated. Things are a little bit different, and so we kind of just focused on M23, the elements of M24 that are in M23, because they're kind of the simplest ones. And so that's how we get the group M23. We started with M24, and then just looked at the simple ones. Okay. And we can write these coefficients in terms of I-Bessel functions and Klusterman sums. And I will show you that at the end, depending on how much time I have. So the first lemma is that if we let delta be -7, then if we divide by 2 times eta cubed, and the reason we want to divide by eta cubed is because we have a weight 3/2 function with the same multiplier system as eta cubed. So we divide by eta cubed, we get something that has no multiplier system and is weight 0. And what we get has a q to the -1. It has a constant term that comes from Mathieu moonshine functions. And then it has terms for k greater than or equal to 1. And this turns out to be a principal moduli for the monstrous genus 0 subgroup gamma of CG. Or again, here are our monstrous elements and genus 0 subgroups. So for some of these elements, it's pretty obvious. So for all the way up through 8, you pretty much automatically know by the structure of these Rademacher sums that what you're going to get, you land in these subgroups and you have the right form of a Q series, that it has to be a principal moduli because it has q to the -1 here and it's bounded at the other cases. But in these 4 cases, it's not quite so obvious because a priori, you only land in gamma naught 11, not gamma naught 11 plus 11. So this plus 11 means that it's invariant under an active linear involution. And so you have to understand how these functions behave under active linear involutions to show that they actually land in these genus 0 groups. So this is kind of the really cool thing, that you actually end up landing in these genus 0 groups. Let me also say that for other delta, you aren't going to land in these genus 0 groups. You're only going to land into gamma naught 11, not gamma naught 11 plus 11. So you can understand that they can't be invariant under these active linear involutions. And so that's why we ended up focusing on just this delta equals -7 case. So what we get is that there exists, as I said before, there exists an infinite dimensional graded representation of M23 whose graded traces are these Tg of tau that come from the previous slide. And so the method of proving this, so there's a general method that comes from Gannon's paper and Duncan, Griffin, and Ono's paper. And so the idea is that we can define these T pi for characters of M23 to be the sum of our graded traces. And if this has non-negative integral coefficients, then there has to exist a module. So really, all we have to do is study these guys and show that they have non-negative integral coefficients. This is kind of a general method for when you have mock modular forms. So how do we do this? So to show that they're integral, we are able to kind of cheat a little bit. Because our functions are the same functions as monstrous moonshine, we already know that the monstrous moonshine functions are what we call replicable. So I'm going to show an example of what that means on the next slide. But really, it's just that if you know the first few coefficients, you can generate the rest recursively. And next, we have to show that they're non-negative. So the way to do that is we can take this expression for the m chi, and we can use the triangle inequality to get this. So if this coefficient from the identity quantity class is much bigger than all of these guys, then we know the whole thing is going to be positive. And so we just have to study the order of growth of all of these coefficients. So here's an example of replicability. So we can, for example, so if we have 4k, we can write it, this is the coefficient of q to the 4k, we can write it in terms of other coefficients in this way. And this translates in terms of these modules as this. So we can generate our modules recursively. If we already know that these modules exist, then we can construct the v of 4k module based off of these. So we've kind of almost constructed it. We haven't quite, because the way that we showed that the first few exist was just checking that the coefficients are integral. But then we can construct the rest recursively using things like this. But it doesn't show that all this does is it shows that there's a virtual module, which means that the coefficients of our t chi's, it shows that they're integral, but not necessarily non-negative, because in the other recursions that are more complicated, there are some minus signs that are not like a minus sign like this that we can deal with. So that's kind of how we do show the non-negativity. Sorry, that's how we show the integrality. So next I want to say just a little bit about the non-negativity. And as I said before, we want to estimate the order of growth of these coefficients. So here's our expression for our kth coefficient. Which again, ng is just the order of the element. We have this I-Bessel function, and we have this Kloosterman sum. And so what we want to do is, the idea is that the c equals 1 term, the first term, is going to outgrow all of the other terms. And the 1a quantity class, the identity quantity class, is going to outgrow all the other quantity classes. So really, if we just take c equals 1 and g equals 1a, that's going to really give us the order of growth, and everything else is just kind of an error term. And so how do we understand this? Well, the Bay bound helps us understand these Kloosterman sums, and a book of Abramovitz and Stegen, which I probably mispronounced, gives very, very explicit estimates for these I-Bessel functions. And so combining the two, we're able to understand the order of growth. And this is much easier than in the case of other moonshine. So in the case that Gannon did, because we have, these are much simpler functions. They're just weight 0. Everything is kind of nicer. And to end, let me just say a couple questions. So this is kind of very preliminary work. So what can we say about the other delta besides -7? What about the other elements of M24? Does this strategy of looking at the columns instead of the rows, is it fruitful for other umbral mock modular forms? Can this M23 module be constructed? What kind of geometric structure does it have? So this is kind of just the first little bit of what hopefully will become a kind of bigger kind of method for dealing with umbral moonshine. Because umbral moonshine with these Mach modular forms is a very hard thing to understand and to be able to construct. And so maybe kind of this method of looking at the columns will make it easier to kind of construct modules in umbral moonshine. So thank you.
Are there any questions for our speaker?
Yeah.
So what kind of bounds did you need to check?
Oh yes, I forgot to say that. Like 10.
Really?
Yeah. So in Mathieu moonshine, you have to check a few hundred. Michael did this. It was a lot of computational work. In this case, the bound that we need to check, where beyond that this term dominates, is something like 10. So once you find out, you're like, oh, I already checked those coefficients, so I'm good. So it's very little kind of computer power that's needed.
Are there any other questions?
So does John Mackay know about this?
I don't think so.
Because he's working.
Uh-huh. Yeah, I don't think so. This is the first time that I've talked about it. Yeah.
Who is we?
Oh, yeah. So, well, mostly the royal we.
Okay, good.
But
Just wanted to-
my kind of advisor on this project was John Duncan. But this is a solo work. Yeah.
That's great.
Are there any other questions? If not, let's thank our speaker again. The last talk is 4:15.
Second class.